topology on this space is precisely the topology induced from X. The norm topology induced from X. Let's recall that at the previous lecture we proved that you have a sequence of a sequence of locally convex spaces such that every xn is closed in xn plus 1, then the inductive limit is not metrizable. So the exercise shows that we cannot drop the assumption that xn is closed in xn plus 1. In this example, xn is dense in xn plus 1, and of course the inductive limit is not only metrizable, but is in fact normable. Okay, so let's now come back to the notion of completeness for topological vector spaces. So we introduced completeness at the previous lecture. Namely, we say that a subset of a topological vector space is complete if every Cauchy net in this subset converges to an element of the same set. If we replace nets by sequences, and by the way, let's recall that a net is something like a sequence, but the difference is that a net is indexed by elements of an arbitrary directed set, not necessarily a set of natural numbers. So if we replace nets by sequences, then we come to the definition of a sequentially complete subset of a topological vector space. In general, completeness is stronger than sequential completeness, and today I'll give you some examples. But at the same time, we discussed a very simple fact at the previous lecture that in the setting of metrizable spaces, completeness and sequential completeness are in fact equivalent. This was a simple exercise for you. Okay, so let's now start with the following fundamental but rather simple result about complete spaces. This is the so-called extension by continuity theorem. Extension by continuity. Suppose we have two topological vector spaces, X and Y, topological vector spaces, and assume that Y is complete. By the way, I forgot to remind you that when we say about completeness, we always assume that our space is Hausdorff. So for non-Hausdorff spaces, we could introduce the same notion of completeness, but it is not very convenient. Many standard results about completeness fail in the non-Hausdorff setting. And this is the reason why we always require that the space we're considering is Hausdorff. So suppose that Y is complete, and suppose that X0 is a dense vector subspace. A dense vector subspace of X. Then, for every continuous linear map, phi 0, which acts from X0 to Y, there exists a unique continuous extension. There exists a unique continuous linear map phi from X to Y, which extends phi 0. So every continuous linear map with values in a complete space can be extended from a dense subspace to the whole space. Probably you know this result in the setting of norm spaces. And here the proof is more or less the same. The only delicate point is to prove the continuity of this extension. So to prove the continuity, we need the following simple lemma, a lemma and an exercise at the same time. So suppose that X is a topological vector space and that X0 is a dense vector subspace of X. Then, first of all, I claim that every neighborhood of 0 in X contains a closed neighborhood of 0. Contains a closed neighborhood of 0. Sometimes this is useful trick. And the second part is about x0. Namely, if we have a neighborhood of 0 in this subspace, say U, if U is a neighborhood of 0 in x0, then the closure of U in x, so we take the closure in x, of course not in x0, but in the bigger space x. So the closure of U in x is also a neighborhood of 0 now in x. The proof is a simple exercise in general topology. Actually, well, the first result easily follows from the axioms of a topological vector space, and the second result is true for any topological space, not necessarily a topological vector space. Now, to prove the extension by continuity theorem, we do the following. Mostly this is a sketch, because the main steps are more or less the same as in the setting of norm spaces. So we take a point in x, little x in x, and since x0 is dense in x, we can always find a net in x0, say x lambda in x0, which converges to x. So it converges. In particular, this is a Cauchy net. X lambda is a Cauchy net. And phi 0 is a continuous linear map from x0 to y. Every continuous linear map takes Cauchy nets to Cauchy nets. So this implies that phi 0 of x lambda is a Cauchy net in y. But y is assumed to be complete. So this net converges to a certain point y, little y, in our space. And now we define phi of x as follows. We let phi of x equal y. It's a simple exercise to show that this is well defined. That is, this doesn't depend on the choice of an approximating net. If we take another approximating net, then we have the same limit here. So phi is well defined. And also it's easy to show that phi is linear, just by construction. So a little delicate point is to show that phi is continuous. To prove the continuity of phi, we start with a closed neighborhood of 0 in y. So the continuity of phi. So let V be a neighborhood of 0 in y. And by using our lemma, we may assume from the very beginning that it is closed. By the first part of our lemma, we may assume that V is closed. If it is not closed, then we simply replace it by smaller closed neighborhood of 0. Since phi 0 is continuous, we can find the neighborhood of 0 in x0. It's a neighborhood of 0 u in x0, such that phi 0 takes u to v. If we now look at the construction of phi here, we see that phi necessarily takes the closure of u also to v. Just by construction, phi takes the closure of u to v. Here we use the assumption that v is also closed. And now we use the second part of our lemma and deduce that this closure is a neighborhood of 0 in x. So the second part of lemma implies that the closure of u is a neighborhood of 0 in x. And this inclusion implies that phi is continuous is continuous at 0, so it is continuous. Phi is continuous. So this proves the existence of phi, and the uniqueness is clear. The uniqueness follows from the assumption that x0 is dense and y is Hausdorff. If two continuous maps to Hausdorff space are the same on a dense subset, then they are the same. Было. Но здесь вроде это не нужно. Тогда пришлось бы брать направленность в пополнении, каждая из них свою направленность в x0, не в пополнении в x, простите. Каждая из них организовывать свою направленность из x можно было бы, ну, там диагональную некую направленность надо было выбрать. Ну, чуть-чуть, ну, не знаю, мне кажется, чуть-чуть дольше. Мне кажется, чуть-чуть дольше, можно и так. So another way of proving the continuity is to use nets in x. This is also possible. Okay. Our next goal is to show that completeness is preserved under some standard constructions of topological vector spaces. First of all, let's look at products. Proposition 1. The product of a family of topological vector spaces, xi, is complete even only if all the spaces xi are complete. In particular, we see that the product of many copies of the base field, k to the power s, where s is any set, which is the same as the set of all functions, the space of all functions on s with values in k, is always complete, because the base field is complete for every set x. And if s is at most countable, then this is a Frischer space. Ks is a Frischer space, that is a complete metrizable locally convex space, if and only if S is at most countable. The proof is an exercise for you. Basically, the left to right implication follows from the fact that every xi is isomorphic to a closed subspace in the product. There are obvious embeddings of the spaces xi into the product, and their ranges are closed. So this shows that the completeness of all the spaces xi is necessary. And to prove the right to left implication, just observe that, look at the definition of the product topology and observe that a net in the product converges if and only if all its projections to the spaces xi converge. And the same and similarly for Cauchy nets. So a net in the product is a Cauchy net if and only if all of its projections onto the spaces xi are Cauchy nets. And that's, this readily implies the proof. Let's now look at projective limits. Projective limits also preserve completeness. More exactly, we have the following fact. If we have a projective system, xi, phi, ij, a projective system of topological vector spaces, of Hausdorff topological vector spaces, and identify the projective limit of this system with a subspace in the product in a canonical way, then this is a closed subspace of the product. In particular, this implies that if all the spaces xi are complete, if all xi are complete, then so is the projective limit. The projective limit of complete spaces is also complete because it is a closed subspace in the product. And the product is complete by proposition 1. Again, the proof is a simple exercise. Just use the standard embedding of the projective limit into the product. So the projective limit consists of all families in the product which are compatible under the maps phi ij. And by using the assumption that the spaces are Hausdorff, I show that this subspace is closed. Before we look at further reconstructions, let's briefly discuss a standard trick for proving completeness. A trick for proving completeness. So suppose that we want to prove that a certain space X is complete. So suppose that X is a topological vector space, and suppose we want to show that it is complete. Assume that somehow we have constructed an embedding of X into a bigger space Y, a continuous linear map. A continuous linear injection of X into a topological vector space Y, which is complete. Suppose that Y is complete. Of course, if this is a topological embedding, then to prove the completeness, it suffices to show that X is closed in Y. But usually, this embedding in concrete situations, this embedding is not a topological embedding. This is also an injective continuous linear map. Anyway, if X lambda is Cauchy net in X, then by the continuity of this map, it is also a Cauchy net in Y. And so it converges in Y. It converges to an element Y, little y in Y. And so we have a candidate for a limit in X. Now to complete the proof, we have to show first that Y, little y, sits in X. And second, that X lambda converges to this limit not only in Y, but also with respect to the finer, the stronger topology in X, which is not the same. Нет, это даже не теорема. This is not a theorem. This is just a kind of argument which is often used in the proof of completeness. I don't explain how we prove A and B, because this depends on the situation. This depends on X, on Y, and on the embedding. But nevertheless, the argument is very standard, and it works in many concrete situations. For example, sometimes it is used implicitly. But to give you just one concrete example, a standard example of using this trick is the standard proof of completeness of the space little p. The completeness of little lp, which you probably know from your functional analysis course. So it's a norm space with respect to the standard norm. It's a standard fact that it is complete. How do we usually prove that it is complete? We essentially use this trick in the setting where X is LP and Y is the space of all sequences equipped with the topology of pointwise convergence. Well, indeed, we take a Cauchy sequence in here, observe that it is pointwise Cauchy, and pointwise Cauchy means that it is Cauchy in here. So it converges pointwise, so we get a candidate for a limit. And then somehow we have to use the assumption that it is a Cauchy once again. And by using this assumption, prove that this candidate for the limit actually sits in LP, and we have the convergence with respect to the LP norm. And actually, there are many other examples where this trick works. Let's now come back to constructions. And let's look at some constructions which involve inductive locally convex topologies. Proposition 3 is about locally convex direct sums. Here we have a family of locally convex spaces. Family of locally convex spaces. Then their locally convex direct sum is complete if and only if all the spaces xi are complete. Well, again, the left to right implication is proved in exactly the same way as in proposition 1. We simply embed every xi as a closed subspace of the direct sum. To prove the right to left implication, this is an idea of proof, apply the trick to the inclusion of the locally convex direct sum into their product. So this is a continuous linear injection. Usually it is not topologically injective unless the set I is finite. If I is infinite, then this is not topological embedding. Nevertheless, this trick works. And to prove A and B, use the standard defining family of semi-norms on the direct sum. Well, I'll recall it now. It looks as follows. We take an arbitrary function. Well, first of all, we take directly defining families of semi-norms on the spaces xi. So for every I, take directed defining family pi of semi-norms on xi. We take a function, an arbitrary function little a on I, and a negative function I, and an element in the product P, in the product of these families of semi-norms. So for any I, we choose a semi-norm in Pi. And we define a semi-norm QAP on the direct sum by the following formula. QAP of an element of this form is, by definition, the sum over I, AI, Pi of xi. So this is well defined because only finitely many elements xi are non-zero. This is an element in the direct sum. We proved some time ago that all semi-norms of this form determine the inductive limit, the standard inductive topology on the locally convex direct sum. So now, if we now come back to this proposition, and if we use semi-norms of this form, we could easily prove both A and B. Actually, in many concrete situations, these parts A and B are proved by the same argument at once. This is a rather standard situation. And the situation works also in this setting. So all the details is an exercise for you. Okay, how about quotients? In general, the situation with quotients is quite delicate, but in the case of Frechet spaces, everything is okay. Namely, we have the following result, proposition 4. So if X is a Frechet space, that is a complete metrizable locally convex space, and X0 is a closed vector subspace in X, then the quotient of X modulo X0 is also a Frechet space. So in the case of Frechet spaces, the completeness is preserved under quotients. I'll give a sketch of the proof. So some details are left as exercises for you. Well, first of all, it's clear that the quotient is metrizable because a locally convex space is metrizable. A Hausdorff locally convex space is metrizable if and only if its topology can be determined by countably many seminorms. But of course, if this property holds for X, then this respective quotient seminorms determine the topology on the quotient. So the metrizability is clear. It's also clear that it's Hausdorff because X0 is closed in X. So the metrizability is clear. Just use quotient seminorms. And to prove the completeness, we do the following. First of all, it suffices to prove the sequential completeness by the metrizability. So we choose a Cauchy sequence, sorry. Let's denote it by xk hat. So suppose this is a Cauchy sequence in the quotient. And let's try to lift this Cauchy sequence to a Cauchy sequence in X. Without loss of generality, we may assume that before we make this assumption, let's choose explicitly defining sequence of seminorms on X. Let's denote them like this. A defining sequence of seminorms on X. So it is countable, and we may assume that it is increasing in the standard way. Just replace the second one by the sum of the first and the second, and so on. Assuming that xk hat is a Cauchy sequence in the quotient, let's find a smaller sequence. And by using this subsequence, we may always assume from the very beginning that the distance between xk plus 1 and xk plus 1 hat and xk hat with respect to the the quotient of the kth seminorm is smaller than 1 over 2 to the power k. Just take a suitable subsequence. This hat here is denotes the quotient seminorm. Now we do the following. First of all, we take an arbitrary representative for x1 hat. We choose any x1 in x1 hat. And then by induction, for every k, we find a representative xk plus 1 in xk plus 1 hat in such a way that the distance between xk plus 1 and xk with respect to the kth seminorm is less than 1 over 2 to the power k. This can be done just by the definition of the quotient seminorm. If we have already chosen xk, then this seminorm is the respective infimum. Since the infimum is smaller than this is the infimum, and since the infimum is smaller than a certain number, we can always choose a representative of this set, which is also less than the same number. Okay, now by looking at this inequality, we deduce that xk is a Cauchy sequence in X. Xk is Cauchy in X. So it converges because X is complete. And by taking the respective elements in the quotient, we deduce that xk hat converges to the respective element in the quotient. And this completes the proof. So once again, I'd like to stress that the key point here, the key point in the proof, was to lift a Cauchy sequence from the quotient to a Cauchy sequence in X. And in general, this argument doesn't work in non-metrizable spaces. And a warning for you, and an exercise at the same time. In general, the quotient of a complete space is not necessarily complete. So if X is a complete locally convex space, and X0 is a closed vector subspace, then the quotient is not necessarily complete. So this doesn't imply that the quotient is complete. Well, some concrete examples will be given as exercises in the next exercise sheet. A few words about inductive limits. Of course, there is no reason to expect that the inductive limit of complete spaces is complete. Inductive limits, in general, they are quite badly behaved. Indeed, we know that even the inductive limit of a sequence of Banach spaces is not necessarily Hausdorff. And moreover, it is not necessarily complete. But at the same time, if we stick to strict inductive limit, then the situation is better. Namely, we have the following fact. The strict inductive limit of a sequence of complete locally convex spaces, of a sequence of complete locally convex spaces, is complete. We'll give the proof later. For technical reasons, it will be more convenient to discuss the proof of this fact after we discuss completions of locally convex spaces. So the proof will be given later. Okay, let's now look at concrete examples of complete locally convex spaces. Oh, before we look at examples, I'd like to say a few words about another construction, namely about the space of continuous linear maps. At the previous lecture, we topologized the space of continuous linear maps between two locally convex spaces in a certain way. Namely, we discussed topologies of uniform convergence. And we had the following fact. Proposition 5. If we have two locally convex spaces, X and Y, such that Y is complete, and X is Bornological. So let's recall that Bornological means that every subset of X, which is absolutely convex and Bornivorous, And Bernoulliverse means that it absorbs bounded sets. So every absolutely convex Bernoulliverse subset of X is a neighborhood of 0. And we know that all metrizable spaces have this property. So if Y is complete and X is Bernoullical, then I claim that the space of continuous linear maps from X to Y equipped with the topology of uniform convergence on bounded sets. So little b means that we consider uniform convergence on the family of all bounded subsets of X. So this space is complete. The proof is also an application of our trick. So we do the following. We take a Cauchy net in the space. So let's denote it by phi lambda. Cauchy net in LB of xy. And observe that this net can be considered as a Cauchy net in the space of all maps from X to Y, equipped with the topology of pointwise convergence. So this implies that phi lambda is Cauchy in Y to the power X. So in other words, we apply our trick to the inclusion of this space into this space. But this space is complete because this is the product of many copies of Y, and Y is assumed to be complete. So it converges. Phi lambda converges to phi in Y to the power X. That is, it converges pointwise. Well, it's a simple exercise to prove that phi is linear. So the property of B being linear is preserved under pointwise limits. Phi is linear. This is a simple exercise. And now we want to show that, first of all, that phi is continuous. And second, that phi lambda converges to phi, not only pointwise, but also uniformly on every bounded set. To prove this, let's write explicitly the assumption that phi lambda is a Cauchy net. So a typical neighborhood of 0, of 0 in LB of xy has the following form. So we denoted this set by M of BU at the previous lecture. So it consists of all those continuous linear maps phi from X to Y, which take B to U, where B is a bounded subset in X, and U is a neighborhood of 0 in Y. And for convenience, we may assume that this neighborhood is closed. U is a closed neighborhood of 0 in Y. Here we are again using the assumption that every neighborhood of 0 contains a closed neighborhood of 0. So when I say typical neighborhood of 0, I mean that all sets of this form constitute a subbase, actually a base of neighborhoods of 0 in the space of linear maps in LB of xy. So now phi lambda is a Cauchy net, and so it is eventually in this neighborhood. So there exists lambda 0 and lambda in lambda such that phi lambda minus phi mu belongs to M of BU whenever lambda and mu are greater than or equal to lambda 0. So let's write this down explicitly. This means that for every x in B, phi lambda of x minus phi mu of x belongs to U whenever lambda and mu are greater than or equal to lambda 0. Now we do the following. We fix a little lambda and take the limit of this net with respect to mu. we take the limit with respect to mu, and we deduce that phi lambda of x minus phi of x. So we remember that phi mu of x converges to phi of x pointwise, belongs to U, formally to the closure of U, but U was assumed to be closed. So it belongs to U for every x in B, and for every lambda greater than or equal to lambda 0. So in other words, this property means that phi lambda converges to phi not only pointwise, but also uniformly on B. And this is true for every bounded set B in X. So we have the uniform convergence on all bounded sets. This is almost the end of the proof, but not exactly, because, well, indeed, we know that phi is linear, and we have the uniform convergence in the space, but we still don't know that phi is continuous. And why is it continuous? Well, if we look again at this uniform convergence, we can easily deduce that phi is bounded on bounded sets. Phi takes bounded sets to bounded sets. This implies that phi of B is bounded in Y for every bounded subset B in X. Well, there is a little argument here, but this is simple exercise. So this uniform convergence implies that phi of B is bounded. So phi takes bounded sets to bounded sets. And now we use the assumption that X is Bornological. And let's recall that if a linear map from a Bornological space to another locally convex space takes bounded sets to bounded sets, then it is continuous. So since X is Bornological, this implies that phi is continuous. And this completes the proof. So in particular, we see, this is an obvious corollary, that for every Bornological locally convex space X, the strong dual X prime beta, so this is the space of all continuous linear functionals equipped with the topology of uniform convergence on bounded sets. So the strong dual is complete. Okay, let's now look at some standard examples of complete locally convex spaces. Example 1. Let's take a locally compact Hausdorff topological space X. Locally compact Hausdorff topological space. So we know, this was discussed some time ago, that in this case, the space of continuous functions, C of x, is isomorphic to the projective limit of the Banach spaces C of k, where k runs over the family of all compact subsets of x. Well, C of k is a Banach space. The projective limit preserves the completeness, and so we deduce that C of x is complete. C of x is complete. The second example, or more exactly, an example and an exercise at the same time. Example exercise 2. Let's now take the space of holomorphic functions. Suppose that U is an open subset of Cn. For simplicity, you may assume that n equals 1. Then the space of holomorphic functions O of U is closed in the space of continuous functions, C of U. But C of u is complete by example 1, and so O of u is also complete. Moreover, it is a Fisher space, because C of u is a Fisher space. It is metrizable because u is second countable. By the way, maybe it's useful to write it down explicitly. So a little comment to example 1. In the setting of example 1, if moreover x is second countable, if moreover x is second countable, that is, has a countable base, then C of x is a Fisher space. Okay, so the space of holomorphic functions is also a Fisher space. Example exercise 3. Let's now look at spaces of smooth functions. We take an open subset U of Rn. And let's take a countable compact exhaustion, Kp, compact exhaustion of U, which means that Kp is an increasing chain of compact subsets, such that the union of this chain is U, and such that every Kp is contained in the interior of Kp plus 1. And let's also assume that the boundary of every such Kp is a smooth submanifold of Rn, such that the boundary of Kp is a smooth submanifold of Rn. The exercise is to show that in this case, the space of smooth functions on U is isomorphic to the projective limit of the spaces Cp over Kp of p times continuously differentiable functions on these compact sets Kp. So each Kp is considered as a manifold with boundary. Actually, we have discussed this isomorphism in the special case where U is the real line and Kp is the closed interval from minus p to p. But this special case easily generalizes to this setting. Well, Cp, the space of p times continuously differentiable functions, is known to be a Banach space. Cp of Kp is a Banach space. And so this isomorphism implies that C infinity of U is a Fisher space. Example exercise 4. Example exercise 4. Let's look at the space little s of rapidly decreasing sequences and at the Schwarz space, script S over Rn. So the exercise is to show that they are isomorphic to projective limits of Banach spaces. Are projective limits of countable systems of Banach space, countable projective systems of Banach spaces. Actually, we have discussed this explicitly in the case of little s when we discussed projective limits. And a similar argument works for the Schwarz space. So this implies that they are Fisher spaces. little s and the Schwarz space are Fisher spaces. Example 5, which is not actually an exercise because of the fact about strict inductive limits. Namely, if we take a second countable Hausdorff topological, locally compact topological space, Hausdorff locally compact space. Then, and we take an open subset U of Rn. Then the space of continuous compactly supported functions on X and the space of smooth compactly supported functions on U are isomorphic to strict inductive limits of Fisher spaces. Strict inductive limits of sequences of Fisher spaces. Just by constructions, by their construction. So this space is actually an inductive limit of Banach spaces of continuous functions with supports contained in a fixed compact set. And this is an inductive limit of Fisher spaces. So since they are strict inductive limits, this implies that they are complete. They are complete. Example 6, which is not entirely trivial, so this is a good exercise. Take the space of holomorphic germs. Let's take a point on the complex plane. So the exercise is to prove that the space of holomorphic germs at this point is complete. We discussed some time ago that it is not metrizable, but it is complete. Let me give you a hint. The hint is to represent the space as a projective limit, which is necessarily uncountable. Projective limit of many copies of little L1. So construct an uncountable projective system in which all the spaces are isomorphic to little L1, and connecting maps are constructed in such a way that the respective projective limit is isomorphic to the space of holomorphic germs. Let me now give you a standard example of a space which is sequentially complete but which is not complete. This example looks as follows. We take an uncountable set S, an uncountable set, and consider the following subspace in the space of all functions on S. So it consists of those functions f on S such that f vanishes, f of S is 0 for all but countably many little s. So in some sense, this is a space of functions with an at most countable support. A simple exercise now is to show that X is sequentially complete. Sequentially complete. And at the same time, it is dense. the space of all functions in S. So since it is dense, we see that it is not closed, and so it is not complete. So it is sequentially complete, but it is not complete. Our next series of examples of complete spaces consists of spaces of distributions. So before we introduce these spaces and prove their completeness, let's prove the following simple proposition about Bernoulligical locally convex spaces. So suppose we have a family of locally convex spaces, Xi, a family of locally convex spaces, and suppose that X is a vector space equipped with the inductive locally convex topology, the inductive locally convex topology generated by a family of linear maps phi I from xi to x. I claim that if all the spaces xi are Bernoulligical, then x is also Bernoulligical. So the property of being Bernoulligical is preserved under taking inductive limits. Not only inductive limits, but arbitrary inductive locally convex topologies. And the proof is very simple. Let's recall that one of the equivalent definitions of a Bernoulligical space is as follows. A locally convex space is Bernoulligical even only if every seminorm on X, which is bounded on bounded sets, is continuous. Well, let's take a seminorm on X. Let P be a seminorm on X such that P is bounded on bounded sets. If we now compose P with phi I, we see that for every I, P composed with phi I, this is a seminorm on xi, it is also bounded on bounded sets. For the simple reason that phi I takes bounded sets to bounded sets. It is continuous, so it takes bounded sets to bounded sets. So this composition is bounded on bounded sets, and this is and xi is Bernoulligical. So this implies that P composed with phi I is continuous for every I. And if you now recall the definition of, well, not the definition, but a simple property of inductive locally convex topologies, so a seminorm on X is continuous if and only if all these seminorms are continuous. So this implies that P is continuous. And this completes the proof. So as a corollary, we see that the space of continuous compactly supported functions on every, well, X is already in use, let's note by T. On any topological space T is Bernoulligical. The space of smooth compactly supported functions on any open set in Rn is Bernoulligical, and the space of holomorphic germs on every compact subset of Cn, so all of them are Bernoulligical. So U is an open subset of Rn, and here T is any topological space. Because just the standard topologies on these spaces are of this form. So the inductive topology here is generated by a family of Banach spaces. The inductive topology here is generated by a family of Fréchet spaces. And the inductive topology here is also generated by Fréchet spaces. Let's now recall that a continuous linear map, sorry, not a linear map from a Bornological space to another locally convex space is continuous, if and only if it is sequentially continuous. So as a corollary, we deduce that a linear functional on the space of smooth compactly supported functions is continuous, even only if it is sequentially continuous. And there is a special name for such functionals. They are called distributions on U. Such functionals F are called distributions on U. The standard Russian terminology is обобщенная функция. Well, I've told you some time ago that in many textbooks aimed for non-mathematicians, the space of smooth compactly supported functions is not equipped with any topology. Instead of that, one introduces convergent sequences axiomatically in the space and defines a distribution to be a sequentially continuous linear functional. So now if we compare this with our approach, we see that a distribution in this sense is just a continuous, in the usual linear functional, which is continuous with respect to the standard inductive topology on the space of smooth compactly supported functions. So the continuity is equivalent to the sequential continuity now, because the space is Bornological. Now our next example of not just an example, but just a set of examples of complete spaces. So the following spaces of distributions are complete. First of all, we can take the space of all distributions, which is often denoted by d prime of U. So, да, сейчас это и напишу буквально через секунду. So the space of distributions d prime of U is by definition the space, the strong dual of the space of smooth compactly supported functions on U. So we take the strong dual topology. So this is the space of all distributions on U. Second, we can take the so-called space of tempered distributions on Rn, which is denoted by S prime. Tempered. Сейчас я напишу это. Обобщенная функция умеренного роста. So S prime of Rn is the strong dual of the Schwarz space. The strong dual of the Schwarz space. Tempered distributions. In Russian, обобщенные функции умеренного роста. Well, why are they complete? This is complete because the space of continuous compactly supported functions is Bornological, and the strong dual of a Bornological space is complete. well, we proved this today, but this is not on the blackboard anymore. Okay, so the strong dual of Bornological space is complete. And for the same reason, well, the Schwarz space is, of course, Bornological because it is a Fauché space. The Fauché space is Bornological. So the strong dual is also complete. And finally, we can take the space of compactly supported distributions, which is often denoted by E prime, script E prime of U. So by definition, this is the strong dual of the space of all smooth functions on U. Где? С компактным носителем. Где? Нет, здесь все короткие функции берутся. Here we take the space of all smooth functions on U. And here we take the space of all smooth compactly supported functions. That's the difference. And in this case, E prime is called the space of compactly supported distributions. The space of compactly supported distributions. On U. It is also complete because the space of smooth functions is a Fauché space. In particular, it is Bornological, so the strong dual is complete. Well, at this point, I don't have time to explain why this space is called the space of compactly supported distributions. Well, very briefly, the reason is that so we have a continuous embedding of this space into this space with dense range. And by passing to dual spaces, we see that the dual of this, which is E prime of U, is continuously embedded into D prime of U, into the dual of this space. So this becomes a subspace in here, not topologically, but just as a vector space. And then there is a standard procedure to introduce the notion of a support for any distributions. In fact, the spaces of distributions over all open subsets of Rn form a sheaf of vector spaces. And so any section has a support. And one can prove, this is a theorem, that a distribution in here is compactly supported if and only if it sits in this subspace. So this is the reason why the strong dual of the space of all smooth functions is called the space of compactly supported distributions. I see it's time to finish. Well, okay, so that's all for today. At the next lecture, we discuss completions of locally convex spaces, prove the existence theorem for completions. In particular, we will represent the completion of an arbitrary locally convex space as a certain projective limit of Banach spaces, which is also quite useful. And as a corollary, we will also prove that the strict inductive limit of a sequence of complete spaces is complete. Okay, thank you. Да, не, чуть раньше. Я даже хотел, чтобы как бы вам разнести немножко. Я думал, вот буквально, может, в течение недели. Да, домашний будет.